All right, so in this question, it says use table 9, where I pasted table 9 right there, to calculate the approximate enthalpy or heat of reaction for the following combustion of 1 mole of methane to form gaseous H2O and CO2. What volume of methane is needed to produce 2,620 kilojoules of heat for methane gas at 29 Celsius and 4.45 ATM. Okay, so this is a very comprehensive problem, incorporates everything. The first thing, when you're given a reaction, always write the reaction. And we should know combustion by now. So we know we're adding O2 to combust anything organic. So CH4 is methane. To combust methane, we're adding O2 to create H2O and CO2 all the time, but it even tells you that in the problem. So that's good. Now we need to balance it. There's 1 carbon here, 1 carbon here. 4 hydrogens here, only 2 of them over here on the right. Have to add a 2. And then the oxygens, we have 2 here, and then 2 from the water, and then 2 from the CO2. That makes 4, so we put a 2 over there. So now it's balanced. Good. So now we need to calculate the enthalpy of formation. All right. Now, yeah. So next, we need to do the sum of the bonds broken minus the sum of the bonds formed. This is how you calculate the enthalpy of formation for a reaction using the bond enthalpies, and this is in kilojoules per mole. So we can do the bonds broken, which is the reactants, minus the bonds formed, which are the products. And this is why it was important to know our Lewis structures and to balance the equation, because in order to find the correct answer, we need to know our coefficients of how many bonds are broken and how many bonds are formed. So for CH4, we're going to have 4 CH bonds, right? Because methane is just a tetrahedral of 4 bonded carbon with 4 hydrogens. So we're going to do 4 times, and we put everything in parentheses, 4 times our CH bond, which is 413. So 4 times 413 plus 2, because you have this coefficient 2, times the O2 bond. And if you remember, the O2 bond is a double bonded oxygen, so that's 498. 498. Okay, and we could put a big parenthesis around all of that, and that is our bonds broken, all of our reactants. Then we're going to subtract all of our bonds formed, which is everything in our products. Now with water, we have an oxygen, and we have 2 OH bonds, and there's going to be 2 of those. So 2 times the water. In each water, there is 2 OH bonds, and then we need to multiply that by 2. So we can put 4 times the OH bond, which is 464. Then we can add our CO2. And our CO2, if you recall the Lewis structure, is carbon double bonded to 2 different oxygens. So we can add 2 times the CO double bond, which is 805. Like that. And that's it. So now we can calculate this. Then this would give us the enthalpy of reaction of 1 mole of methane's combustion, right? Because the coefficient in front of methane is 1. So let me calculate that real quick. This is 2,648 minus 3,466. This is going to be negative 818 kilojoules per mole of methane. And this makes sense. The reason why it's combustion. Combustion, what happens when you burn something? Heat is released. A lot of heat is released. So this number has to be negative. If you see combustion and then you calculate the enthalpy of reaction and it's positive, you did something wrong. So it's definitely negative. Next part of the question is, what volume in liters of methane is needed to produce this much heat for methane gas at these properties? So we know per mole we have 818, but to produce 2,620, how many moles do we need? The reason why I'm thinking in terms of moles is because the information given and the information asked for is liters, and given we have temperature and pressure. So the equation that comes to mind is PV equals nRT. We have our pressure, we're looking for our volume, we have R and we have T. We don't have our number of moles, but it's giving us the clue that we're trying to figure out what volume of methane is needed to produce this much heat. Well, we know that each mole produces 818. So what we can do is 2,620 divided by 818. Doesn't have to be negative because they're being released. 2,620 divided by 818. And we have 3.20 moles of methane. That's how much methane is responsible for this much heat produced. So now we can put that N, number of moles, into our PV equals nRT to figure out our volume in liters. So our pressure is going to be 4.45 times our volume equals 3.2 times 0.08206, because we're using this constant because it's liter ATM per Kelvin mole, multiplied by our Kelvin temperature, which is 29 plus 273. That's 302. And then we do the math here. So 302 times 0.08206 times 3.2 moles divided by 4.45. And that gives us our volume liter, or our volume V equals 17.8 liters. And that's the correct answer. So this is a good question. It goes over kind of everything from stoichiometry to bond enthalpy to gases. It's a really good question.